Hello everyone. Hello everyone. Welcome to Sai Tutorials Jamkandi. So in our tutorials, 10th class Kannada medium, English medium, as well as 8th and 9th regular classes as well as online classes. So subjects are mentioned in the page. So please do subscribe our channel and please join us to learn more the things. So dear students, I'm going to handle in this session, that is physics second PUC chapter, that is third chapter. So in the previous sessions I have completed the first chapter and third chapter, first and second chapters. So this is the third chapter. So in this today's session, let us learn about the introduction part related to the third chapter, that is electric current. Okay, in this chapter let us learn about the current electricity. Okay, so dear students, you know about the current and what is current, what is electricity in the I mean in the general, like general, uh, you know about it. Okay, generally you know something about what is electricity and what is current and like that. Okay, am I right or not? Right. See, let us learn this in physics, how this will uh, going to happen in the, you know about conductors, electricity and current, how it will going to happen and how it will transfer of charges and etc. So in this today's session, let us learn about the exact physical phenomenon. Okay, the exact physical phenomenon relating to the current, electricity. So first of all, before coming to the electric current, so we need some kind of charges. Am I right or not? Okay, we need charges. If there are no charges, there will be no electricity. Okay. The Let us come to the part that is charges. Okay. See, charges in a motion. Okay. These charges in a motion constitute an electric current. If there is no charges, is there any a kind of electric current? I mean, is there any the passage of electricity over the any object or any conductor there? No. See, suppose the charges will, if suppose the charges are in motion, then only there will be a kind of electricity will going to happen. See, a conductor offers a path for current, which offers a path for current to flow in that conductor. They see the conductor only itself. The conductor itself offers a path for current. So application of potential difference across a conductor causes current. I have discussed in the earlier session about the potential difference across the any conductor. So these causes a current. And potential difference can be provided using a cell or a battery. How would you provide? How would you provide for electricity to flow? The potential difference can be provided with the help of, I mean, in the form of cell or a battery or a group of cells. Battery in the sense a group of cells. Now, the flow of electric charges. Okay. Electric current. Okay. Electric current. The flow of electric charges in a conductor constitute an electric current. See, what do you mean by electric current? In the general sense, the flow of electric, please note on this, The flow of electric charges in a conductor. In a conductor constitutes electric current. Please note down this. The general definition for electric current is the flow of electric charges in a conductor constitutes an electric current. See, flow of charges in a conductor can be compared to the flow of water in a river. Suppose how the river will flow like this. Okay, this is a river. How the river will flow? See, the flow of charges in a conductor can be compared to the flow of water in a river. So, German physicist George Simon Ohm considered it as a electric current similar to heat flow in a conductor. Who? The physical, the physicist, one of the German physicist George Simon Ohm. This is just a general introduction. Considered electric current similar to flow heat flow. Heat flow in a conductor. Okay, this is just a general part related to the concept. See, the flow of electric charges in a conductor constitutes electric current. See, this flow of charges we can be compared to the flow of water. You can consider how the water will flow in the river like that. The flow of charges will take place in a conductor. So, the German physicist George Simon Ohm considered electric current similar to the heat flow in a conductor. Heat flow in a conductor. See, I have told you that charges in motion constitutes an electric current. Okay, charges in motion constitute an electric current. So, conductor offers a path for current. Application of potential difference across a conductor causes current. So, potential difference can be provided using the cell or a battery. Battery in the sense a group of cells. Okay, current in a circuit in a single direction is called direct current. DC. What do you mean by DC? The current. The current in a See the current. This is the current in a circuit. The circuit current in a circuit in a single direction, in a same direction, it is called as a direct current. While a current whose direction keep reversing at regular intervals and whose magnitude keeps changing continuously is called as a alternating current. They will ask in the examination, what do you mean by direct current and what do you mean by alternating current? See, a current in a circuit, okay, a current in a circuit in a single direction is called a direct current, while a reverse direction having the regular intervals and whose magnitude keeps changing continuously is called as a alternating current. This is to be noted down. Okay. Now coming to the current carriers. Now coming to the current carriers. See, what do you mean by current carriers? Mobile charge carriers. Mobile in the sense. Those are in the motion. Those are in the motion. They can be transferred. I mean, they can move in anywhere. I mean, they can move from one place to the another place. Okay, charge carriers are the mobiles, are also called as a mobile charge carriers. The charged particles whose drift in a definite direction constitutes a electric current. So such a current are called as a current carriers. Those are called as a current carriers. Okay. These charged particles whose drift will takes place in a definite direction constitutes the electric current. So such a current carrying conductors, I mean such a current carrying charges are called as a current carriers. Okay. So let me discuss in a wide part. So dear students, current carriers are also called as a mobile charge carriers. Okay. I have said you charge carriers. Current carriers, or these are also called as mobile charge carriers. Mobile charge carriers. Okay. Whose drift will takes place in a definite direction. So such a charges are called as a current carriers or mobile charge carriers. So these charged particles which constitute an electric current in this will takes place in solids, liquids, or in a gases. Okay, are known as a current carriers or charge carriers. See, charge carriers where current, electric current in a solids, liquids, or gases are known as a current carriers or charge carriers. Which are the charge carriers? Those are the takes place in charged particles which constitutes an electric current in solids, charged particles which constitute an electric current in solids, liquids, or gases are known as current carriers or charge carriers. Okay, then see, first of all, I'm going to take a solid, okay, solid conductor. See, solids can be conductors. These can be, I have told you in the previous session what is conductor, what is insulator, and what is semiconductor. I have told you. See, these can be, okay, solids can be conductors, insulators, or semiconductors, or semiconductors. See, conductors in the sense, if you take for example any metals in the form of solids, any metals like copper, silver, silver, aluminium, etc. So in that case, free electrons or valence electrons are in the form are called as current carriers. So in that form, free electrons or valence electrons are the current carriers. Suppose if you take an insulator, okay, if you take an insulator, all the electrons are tightly bound to their parent atoms. Am I right or not? See, or in case of insulators, all the electrons are tightly bound to their parent atoms. Hence, they do not have any free electrons, and such there is a practically no current carriers in an insulator. See, the word itself indicates insulators are as where insulators which do not conduct electricity. Such a property it is called as insulators. Why it will happen that and all the electrons are tightly bound to the parent atom, hence there is no any free electrons. As such, there is a practically no current carriers in an insulator. If you take for example semiconductor, the current carriers are free electrons and hole. Okay. If you take semiconductors, if you take for example semiconductor, what are the free electrons here? Those are electrons and holes. In case of semiconductors are the free charge carriers or current carriers. Here, and if you take for example, liquids, okay, liquids also conduct some kind of electricity to pass through them, and see such examples are called as copper sulfate, silver nitrate solution, copper sulfate solution and silver nitrate solution, and NaCl, I mean sodium chloride solution, H2SO4, etc., hydrochloric acid, etc. Okay, in gases also behave as a insulators of electricity. But if you consider gases, gases see, gases behave as an insulators. Insulators in the sense they do not conduct any a kind of electricity to pass through them. So therefore behaves as insulators of electricity, but they get ionized and becomes conductor at a low pressure. At a low pressure. When they will conduct electricity at low pressure, they get ionized and become conductors. So when high potential difference is applied across them, and also we need to keep a high potential. Okay, we need to keep a high potential difference is applied across them. Ionized gas contains the positive electrons and electrons, which are the current carriers in case of gases. Okay, ionized gas. Those ionized gas contains positive ions as well as electrons, which are the current carriers in gases. Okay, dear students, we have learned in deep, that is charge carriers or current carriers or mobile charge carriers. These will take place in a solids, liquids, and gases. If you consider the solids, conductors, those insulators or semiconductor type of metals are there. So, metals like copper, silver, aluminum, etc. So, insulators in the sense they do not conduct any electricity. Okay, all the electrons are tightly bound to their parent atom, hence there is no any kind of free electrons, so they act as a insulators where no current carriers are present in the insulators. And if you consider the semiconductor, the current carriers are electrons and holes. Okay, and if you take into consideration that is liquids which allow the electricity to pass through them and consequences dissociate ions into ions, those are called as electrolytes. We call it as electrolytes. If you consider the copper sulfate solution and AgNO3, I mean silver nitrate solution, these are the conductors of electricity, as well as sodium chloride solution or sulfuric acid solution. So these are called as a which allow the electricity to pass through them in case of liquids. And if you consider the gases, okay, if you consider the gases which behave as a insulators of electricity, but they get ionized and become conductors. They get ionized and become conductors at a low pressure, and also when high potential difference is applied across them, then only they will converted into conductors. So those ionized gas contains positive and negative electrons. I mean positive electrons, positive ions and electrons. So those positive and electrons are called as a current carriers in case of gases. Current carriers in case of gases in the sense the positive ions and electrons. This is a deep discussion about the current carriers. I hope this concept is clear to you. Okay, current carriers is completed. Now, coming to the conventional current. Okay, conventional current. What do you mean by conventional current then? See, See, conventional current. In a metallic conductors, okay, in a metallic conductors, negatively charged particles, namely electrons. Am I right or not? Okay, and these electrons drift under the influence of applied potential difference. This constitutes an electric current. Okay, this constitutes an electric current. The direction of drift of positive charges is the direction of current. This current is called as a conventional current. I hope this is very clear here. See, in a metallic conductor, suppose if you consider the metallic conductors, so whatever the negatively charged particles, okay, whatever the negatively charged particles which are also called as electrons, okay, which are also called as electrons, so those electrons will drift under the influence of applied potential difference. Drift in the sense they'll start passing, I mean they will start moving each other, they will start drift, I mean drift under the influence of applied potential difference. So whatever you apply the potential difference in the conductor, the electrons is going to be drift. Okay, so this constitutes an electric current. So the direction of drift of positive charges is the direction of current. So whatever the direction is there, no, the direction of that drift of a positive charges, whatever the positive charges are going to drift in the direction of current, so that current is called conventional current. Anyhow the drift will takes place uh, by the electrons present in the conductor, but the direction of drift of positive charges, the direction of drift of positive charges is the direction of current. Okay, so this current, so that current, the drift of that positive charges in the direction of current, so that direction of the current is called as a conventional current. Okay, the direction of conventional current is opposite to that of electrons, opposite to that of electrons. Suppose hmm, suppose if I consider any conductor here which is having the negatively charges, okay, which is having the negatively charges, which is having the negative charges as well as positively positive charges. If you apply some potential difference across that conductor, so if you apply the potential difference across that conductor, the negative charges will drift. Okay, the negative charges will start moving. Okay, in the conductor, the potential, due to the potential difference whatever you have applied. Okay, this constitutes an electric current, we know that. Okay, but the direction of drift of positive charges is a direction of current. So whatever the direction is there, no, I mean suppose if the electrons are moving like this, if the suppose if the electrons are moving moving line like this, that is negative charges, but whatever the drift of positive charges will take place opposite to the direction of electrons. So that direction is called as that direction of will show the direction of current. Okay, that direction will show the direction of current. So this direction is called as conventional current. So the direction of conventional current is opposite to that of drift of electrons. The opposite to that of drift of electrons. So this is called as conventional current. So in the direction of flow of positive charges, in the direction of opposite to the flow of negative charges will takes place. This is called as a conventional current in metallic conductor. Okay. Just so I hope this concept is clear to you. Now if you go for the strength of electric current, okay, the strength of electric current. See, What do you mean by strength of electric current? See, electric current, we have learned about what is electric current. So it is the net flow of charge per second. Okay, it is a net flow of charge per second across a surface. So if that, so let me discuss you with a proof. See, electric, we have learnt about electric current, right? See, now let us discuss about the strength of electric current. What is the strength of electric current? Please note down this. See, it is defined as the rate of flow of electric charges through a cross section of the conductor. Okay, it is a rate of flow of, it is defined as rate of flow of electric charge, rate of flow of electric charge through cross section, okay, cross section of a conductor, of a conductor, which is called as electric current. See, suppose let us consider a conductor. Let us consider a conductor. So whatever the electric current is defined as a net flow of charges, whatever the charges are flowing inside the conductor per unit, per unit time, okay, per unit time through a cross section of that conductor. These are the charges. Am I right or not? So electric current, that is I is equal to total current, total charge. Okay. Please note down this, total charge flowing, that is denoted as Q divided by per unit time, that is denoted by T. Okay. So what is the charge of the electron? Charge of the electron is 1.6 into 10 to the power of minus 19. So across each section of a conductor in time t, then that charge q is equal to number of charges, and this is the charge of the electron. Okay. Where if you substitute, suppose if you substitute in the conduct current, if you substitute in the current q by t, what is q? N into E divided by T. Okay, this is all about the strength of an electric conductor. Strength of the electric conductor. Suppose electric current is a net flow of charge per second, that is I is equal to, that is I is equal to Q divided by T. Okay, if del Q is the amount of charge that passes through an area in a time interval delta T, then the average current in the given interval can be written as like this. Okay, this is the average amount of charges passing through the area to the at a average time interval delta T. So the instantaneous current is given by I is equal to limit delta T tends to 0, that is delta Q divided by delta T, or it can also be written as a for a small surface area, for a small area of the conductor, that is differentiation of that charge to that of T. So if the current is steady, I have told you, if this current is steady, suppose I have considered a conductor with a charge flowing through that conductor with a suppose that charge is passing through that conductor per unit time. So per unit time, where Q is a charge flowing across a section of a conductor in an interval of time t, and the SI unit of current is ampere. Okay, ampere, 1 ampere is equal to 1 coulombs per second. Coulombs per second. Okay, so 1 coulomb is equal to how much? 6.25 into 10 to the power of 18 electrons. So a flow of 6.25 into 10 to the power of 18 electrons per second is equal to 1 ampere of the current. Okay, 1 ampere of current. So I hope this concept is clear to you. This is about the strength of electric current. So, some kind of examples I'm going to tell you that. So these are materials and these are the metallic charge, mobile charge conduct carriers. I have told you in the, just a second, I have told you metallic conductors. In metallic conductors, free electrons are the mobile charge carriers. In liquid conductors, I have told you positive ions and negative ions, electrons. In semiconductors, free electrons and holes. Gaseous conductors, positive ions and free electrons. In gaseous conductors, positive ions and free electrons. In superconductors, Cooper pairs, a pair of electrons with the opposite spins. Okay, in superconductors, Cooper pairs will take place. Those are a pair of electrons with the opposite spins. These are all the charge carriers and their materials. So dear students, I hope this is the introduction part is clear to you. So whatever the concept I have left, I will cover it in the next session. So this is all about the deep introduction about the current electricity. So by this, I am going to wind up this session today itself. So in tomorrow's session, let us discuss whatever the concept related to your syllabus. I'll discuss in the tomorrow's session. So dear students, today we have learnt about what is electric current, how we need to pass the electricity to the conductors by providing the potential difference across that conductor using a cell or a battery, and what is direct current and what is alternating current, current carriers, mobile charge carriers in case of conductors, insulators and semiconductors, and also conventional current in a metallic conductor, and strength of electric current, how it is going to vary with the time and with the how much amount of charges are going to flow in that conductor, like that. So and also the small concept, that is materials and their uh, corresponding mobile charge carriers. So in the tomorrow session, let us learn about what is current density and further information related to the concept. So I hope this session is clear to you guys. So please don't forget to subscribe our channel. Just learn more and reach your goal. Thank you.